Hello and welcome to physics. We are going to look at work, energy, and power. Then we will be looking at energy. So, what is energy? Energy is defined according to work. Okay, so energy is measured in joules, and whenever work is done, energy is transferred. So I cannot do work without transferring energy, and therefore we define energy in terms of work done. So energy is present whenever work is being done. So therefore, if objects have energy, work is being done on the object or by the object. Okay, so if an object is moving, either the object is being work is being done on the object or work is being done by the object. Okay, so if it's a car, the car does the work to drive, but if it's an object busy moving, I have to push the object because the object doesn't necessarily have an engine. Okay, so let's look at work done and energy transferred. Okay, so here the guy is lifting up a stone 2 meters. Okay, so we will look at gravitational potential energy, and in that we will use the constant G, as we can see at the bottom. Now it depends whether you're doing AS physics, IG physics, or mechanics. So in AS physics, we know we're using G as 9.81, but for practical purposes, or for other purposes, for IGCSE and mechanics, we use 10. Okay, so in this example, they is an AS physics example, they use G as 9.81. So if we take the 1.5 kilogram mass and we times it with G, we get the weight. If we multiply the weight, as if we think in terms of work done, the force is the weight being lifted, and the height is 2 meters. So if we take the 1.5 times G times the height, we get 29.4. That's if G is 9.81. Okay, obviously it would be 30 if G is 10. Okay, if we look at the gravitational potential energy, we're going to look at the formula now. It's mass, gravity, height. So if the mass is 1.5, if we use G as 9.81 and the height is 2 meters, we get the same answer. And here we can see that the amount of work done is equal to the amount of gravitational potential energy transferred. Now we will see later, if he releases that stone, energy is released in terms of kinetic energy, and that is also work being done. Okay, so guys, just before we move on, we have to just think about what is the different types of energy. Although we're only going to look at two in this topic, we just need to know everything, or just go through it. So the heat energy is energy transferring heat. Okay, so whenever objects lose heat, whenever objects gain heat, it's the energy of transferring heat. Okay, so next one, kinetic energy is the energy of movement. Whenever objects move, they have kinetic energy. Nuclear energy is a form of energy from the nuclei of atoms. So whenever there is changes in the nucleus, nuclear energy is released, and that's where we get nuclear radiation from and radioactivity. Okay, sound wave is the energy of sound waves, guys. Sound is a form of energy that travels in terms of a wave. Light is also a form of energy that travels in waves, so it is energy of light waves. Chemical energy is any energy resulting from a chemical reaction. Now, even when I burn wood, that is a chemical reaction, and therefore fire is the visible representation of that energy, and it is a form of, it's because of a chemical reaction. Electrical energy is energy due to electrons moving. Now, whether it's static electricity or whether it's electrical, like normal current electricity, like what we have in our houses, electricity is due to electrons moving from one point to another, either because two objects have been rubbed against each other, or because there is a cell giving energy to electrons to move through a circuit. Okay, then we get gravitational potential energy, and that's energy due to the object being lifted to a certain height inside a gravitational field. Now, in space, because there's no gravity, then there won't be any gravitational potential energy. And lastly, elastic potential energy is the energy of stretching anything or compressing anything. So if you think of a spring, sometimes springs can compress and springs can stretch. Both ways, either stretching or compressing, is a form of elastic potential energy. Okay, so what is kinetic energy? Any object that moves will have kinetic energy. The amount of kinetic energy an object has can be found using the following formula, where the kinetic energy in joules is half the mass in kilograms times the velocity squared, or EK is half mv squared. Okay, so if we have look at our aeroplane has a mass of 40,000 kilograms, a velocity of 242 meters per second. We square our velocity and we times it with our mass and we times it with a half, and we get 1.17 times 10 to the 9 joules. Okay, so we use scientific notation there just because it's such a big number. Okay, so let's look at a few easy examples. Remember the formula is half the mass in kilograms times the velocity in meters per second squared. Okay, so Katie drives a car at a speed of 30 meters per second. If the combined mass of her and the car is 1,000, what is her kinetic energy? So half the 1,000 times 30 squared gives me 450,000 joules. Ben rides his bike at a speed of 10 meters per second. If the combined mass of Ben and his bike is 80 kilograms, what is his kinetic energy? So that's half times 80 times 10 squared. That gives us 4,000 joules. Will is running and has kinetic energy of 750 newtons. If his mass is 60 kilograms, how fast is he running? Now here you have to concentrate because in the formula, half mv squared, so the velocity is squared, so we're going to square root our answer. We first get rid of the half, so we times 750 by 2, that gives us 1,500. Then we divide it with 60, that gives us 25, and we square root our answer. 25 squared gives us 5 meters per second. Now I can always test this answer. Half of 60 times 5 squared should give me 750 again. Then you can know you're right. Connor is walking to town. If he has kinetic energy of 150 joules and he's working at a pace of 2 meters per second, what is his mass? So we times the 150 by the half, by 2 to get rid of the half, so that's 300, and divide it by 2 squared, so we say 300 divided by 4, and that gives us 75 kilograms, and that is basically an average weight for an adult male. Okay, so gravitational potential energy. If we try to work out how much gravitational potential energy an object gains when it is lifted, we would use a simple equation. The energy of gravitational potential energy in joules, its weight in newtons times the change in height. Or instead of weight, we can say mass times gravity. Now remember, if we think of G, if you're doing AS physics, you're going to use 9.81. If you're doing IG physics, G is 10. And if you're doing mechanics, G is also 10. Okay, so we will look at, and from here on, we will look at G as 10. Okay, so we have a triangle here, which we can also see how we can use that. Okay, so let's quickly look. Remember, gravitational potential energy is not just when objects go higher, but also when they fall, then they're losing gravitational potential energy. So I either gain gravitational energy by going higher, or lose gravitational potential energy by going lower or falling. Okay, so a brick weighs 10 Newton. The weight is already calculated and lifted to a top of a house of 10 meters. So mass times gravity is already given as 10 times 10 gives us 100 joules. A 1,000 kilogram car lifted by a ramp up to a height of 2 meters. Now that's very scary if you lift your car up 2 meters. Okay, so mass is 1,000, gravity is 10 times 2, so that's 10,000 times 2 gives us 20,000 joules. A 70 kilogram person lifted up 50 centimeters by a friend. Okay, so half a meter, you have to convert your 50 centimeters. Okay, so 70 times 10 is 700 times a half gives us 350 joules. Okay, so how much gravitational potential energy is lost in the following situations? A football of 2 Newton is dropping out of the air after being kicked up 30 Newton. So we just want to know, 30 meters. We just want to know how much energy is lost from the highest point to the ground. So the weight is already given, mass times gravity, and then we times it with the 30, which gives us 60 joules. A 0.5 Newton egg falling 10 meters out of a bird's nest. Once again, they give us the weight. So the weight times the height, or mgh, gives us 5 joules. And then a 1,000 kilogram car falls off a 200 centimeter ramp. Now 200 centimeters is 2 meters, and that's exactly the opposite of what we initially had, and that is 20,000 Newton. Joules, 20,000 joules. So, potential energy becoming kinetic energy. Okay, so guys, when objects fall, the potential energy becomes kinetic energy when it falls from rest and lands directly on the ground. So here we could see the object has, due to its height, a certain amount of potential energy. As it falls, it starts from rest and it accelerates downwards and goes faster and faster and faster. And when it hits the ground, just before it hits the ground, that's why it's not zero yet, we get that basically all the gravitational potential energy is turned into kinetic energy. In this example, they're using gravity, G as 9.81. Okay. So conservation of energy equations in the ideal situation. So what does it mean, ideal situation? It means when there's no energy loss. So whenever there is no energy loss, meaning there is or energy gained due to a applied force. So there's no applied force and there's no energy loss due to friction, heat, sound, or anything like that. We know that the total energy in the system cannot be created or destroyed if there's no influx of energy or no loss of energy. Therefore, the total energy in the beginning must be equal to the total energy at the end. So the sum of the potential and the kinetic energy in the beginning is equal to the sum of the kinetic and the potential energy at the end. Now we call this sum of potential and kinetic energy, some syllabi refer to it as mechanical energy. Okay, and I've always said it's like a hourglass, okay, where inside the one side is potential, the other side is kinetic, and the energy is the sand inside. So we will see that either our energy will be only potential at the highest point before it falls, or either our energy will be only kinetic at the lowest point before it hits the ground, or anywhere in between. It's the sum of the kinetic and the potential. So if we look at the following example, the total energy or the mechanical energy initial is equal to the total or the mechanical energy finally. So to get the initial energy, we know at the highest point it starts from 0, so the kinetic energy is 0, and the energy is due to its height. At the bottom, the height is 0, so there's 0 gravitational potential energy, but the energy is due to its speed. So the car hits something there at the bottom. Okay, so the total mechanical energy at the top is equal to the total mechanical energy at the bottom. And in short, in a scenario like this, if there's no friction, no applied force, then the potential energy at the top is equal to the kinetic energy at the bottom. Okay, now if you're doing AS physics or mechanics, you might ask, how does conservation of energy fit in with UVAST or Stewart equations, the equations of motion? So there we look at the gravitational potential energy at the top is equal to the kinetic energy at the bottom. mgh is equal to half mv squared. Okay, if we see that it's the same object, okay, so it's the same mass, therefore we can cancel out mass. And then if we rearrange our equation, we get that the height, which is s, is v squared over 2g. Now the initial, or u, is 0, so S is v squared minus u squared over 2g, which is 2a. And that comes from the equation of motion that says v squared is u squared plus 2as. It's just a different variation of that formula. And then we can calculate the velocity there, square root of the velocity, and we get the velocity is square root of the velocity squared, and then we get that the velocity is 4.43 meters per second. Okay, now guys, if we see graphs, a lot of times they give us energy graphs, energy and time. Here we've got gravitational potential energy. So as the bouncing ball, as the ball drops and then bounces, we see that the potential energy becomes less and less and less. The moment it bounces, the potential energy is 0, and then it gains potential energy again up to a maximum, and then it bounces again, goes down, and then it comes up and goes down again, and it will continue to do so until all the energy is run out. The fact that the bounce is less potential energy each time means that there is energy lost due to sound or due to friction or something like that. Now, or even the changing the shape of the ball, elastic energy. Okay, so if we compare the kinetic energy at the highest point, okay, when I've dropped the ball, it's got 0 kinetic energy. Just before it bounces, okay, the kinetic energy is the highest. And then as it bounces, the kinetic energy decreases again up to the highest point where there's 0 speed, and then it falls again, giving more kinetic energy. And if we combine these two graphs, we see that the total energy each time decreases due to a loss of energy, but we can see that as the same amount of, in the same form, same shape, the potential energy decreasing is the kinetic energy increasing. And therefore, like I said before, the total energy is the sum of the kinetic plus the potential energy at any given period of time. Okay, that's a brief summary of work or energy or power, or all three. I hope you have understood this, and if you've got any questions, please leave me a message. Thank you.